Okay.
Okay. All right. Good evening, everyone. It's nice to meet everyone again. Okay, so we're going to review what is ANN again. Again, in layman's term, when we say artificial neural network, it's almost similar to SEM. It's just that it has hidden layers. So input layers, meaning we have to we're talking about our latent variables for input layers. For hidden layers, it's what like Doc Yogi mentioned last week. It's like block box. So you don't really know what are the factors or what are the latent variables that the code will input in our hidden layers. Output layers are our intention to visit, intention to donate and intention to visit the turkey. Then for biased neurons, it's always one for input layer and always one for hidden layer. Why? Because it assists us into finding what are the factors that we have yet to consider. And again, the difference between the two is that for artificial neural network, we only have one hidden layer. But for DNN or deep neural network, we have multiple hidden layers. And don't forget as well to install this one through Anaconda. So you should always look out for this one. The one without PowerShell prompt. Just this one and then run as administration. Okay. And then you can just type the pip install here. Okay. And then through Anaconda, I'll show our code last time. So this is our code last time. We've already talked about from this part up until this part, but just to recall again, when we say import and from, we wanted to establish the code for ANN. For example, when we say numerical Python and pandas, they always come into one package because it's like your operations or your code in order for you to multiply, to add, to subtract, and to divide all your arrays or all your data in a table format. And then for Matplotlib, it's about extracting the possible codes from the MATLAB that we have um this one the MATLAB that we have utilized from the PSO, because if you could still recall, we did not import any package for the MATLAB, but unfortunately for the Python or the Spider package, we have to import all of the codes that we needed to fill in order to run the ANN. TensorFlow is needed for ANN, as well as Keras, and of course our sklearn model, which is train test split. So whenever we have to choose our training and testing split, it's always important to have the 50 is to 50 training testing split, or 60 is to 40, 70 is to 30, 80 is to 20, 90 is to 10. It's always the usual combination. It's just really a matter of finding the perfect combination among all of them. So again, from this part up until this part, it's all about setting up all our data from the CSV file or from the Excel file. And then for this part, we wanted to know which factor we would like to assess. So in our data, let's say we wanted to assess this part, the EE. We wanted to assess EE latent variable, so you have to input EE here. And then you should only have one target variable or one dependent variable for this part. That's why we only have to focus on ID. Okay, so later on we can change them. We can change them as EE and then IV. It's totally fine, but you have to run all the model first. Okay, so just for an example, let's evaluate intention to donate first. And then similar to this one, this should be ID, because when we say label, we're talking about our target variable or dependent variable. And features, before mainly pertain our we mainly call our latent variables as latent variables, but in ANN, it's always called as features. So you might mix your words a bit, but you really have to call it as features once you write it in your research paper, because some reviewers might also feel, let's say, uh
Strange if they don't use
yes.
the word feature.
Yes,
Like
they
latent selection. Like, wow,
yes,
that's
they
very
might
weird.
not know it. Yes, that's correct. And then, okay. So yeah, it's these codes are all about calling out our training and testing split. So again, you also have to adjust this part. Training set, testing set. Sorry, testing set. It could be anywhere from, I'll just input it here, 50% or zero point 0.5, zero point 0.4, zero point 0.3, zero point 0.2, and zero point 0.1. And similar to this part. Mhm. Okay. Why are why should we call out both of them as testing set and not training set? Because in this code, it's already automatic. If you have testing set of 40%, then the code will automatically realize that you have 60% for the training variable, similar to the another one. Okay. So let's continue our code. So now that we already have our data, the next stop for us is all about ANN parameters. So from this part, creating our model, up until the last part, it's all about curating our ANN model. Okay, so let me copy this one and then let's discuss one by one. So for this line pertains to our input layers. If we're going to go back to our guide, this is our input layers. So this is your code for your input layers. And again, what are our input layers? These are our latent variables. We have a total of, if we're going to count it, we have a total of 11 latent variables. But we have removed EE, right? We have removed EE because we wanted to check it if it's significant from the model. Again, because in ANN, the thing is with ANN, it removes what you wanted to check having that significance factor. That's why you only have 10, 10 latent variables or 10 features. But in our code, you also have to include your target variable, which is your ID. So instead of inputting 10, you have to add one more. That would be 11. Mhm. So that's why your input variable over here should be 11. This should be 11, and then this one as well. But this would not run. I'll check it. I'll copy the rest so that we can check it if it will run. Okay, if you notice, it has a lot of error. Why? It actually the error came from this part. I'll remove the other parts again. Later on. I'll remove the other parts because we have called them out as 11. It turns into error because we have a total of how many columns? It has a total of 13 columns. But you only need a total of 12 columns. Why do you need a total of 12 columns? Because first, you have eliminated EE, but it is considered in the model. Next, you have considered everything until ID except for IV. That's why you have to eliminate this part first. So let's eliminate this part. I'll save it
So it
here.
cannot be like together, Myla.
Mm, Yes, it should be in a different
Oh,
Excel sheet.
I see. This one I don't know.
Yes.
Yeah. Okay, okay.
Okay. So you can treat it like this one first, and then let's click. Let's try it again if it's going to run. Okay, so it ran already. So as you have noticed, you really have to make your Excel work in order for you really have to make everything coincide with each other. But the thing is, you can also include the other one. Let's say you wanted to focus on evaluating the ID without considering these target variable. It's possible, but if you wanted to apply the concept of structural equation modeling wherein you can also get a little bit of factors or significant factors from IV, you can also input this one. Let's go back again. But then again, you might have a lesser accuracy once you input these IV. It's just a hypothetical model because it's like once you input a lot of features, some of your accuracy models might also decrease. So you can is just in case you wanted to include IV, it's also fine, but you have to include 12. Okay. So let's run it. But for me, I would personally exclude IV so that you can attain a higher accuracy model. Mhm. Wait a minute. Where is the error? Number 2. Mm, I'll save it. I'll save this one. Oh, sorry. Oh, I'm sorry. This is the error. I forgot to input it into 12. So just in case you wanted to, again, include your IV, you can just input it as 12. All right, so it's working now. Okay. So let's proceed. I'll remove them again. Again, that's your input layers. For your hidden layers, it's actually dependent on you. You can choose anywhere from 10 to 100. Usually for 500 something respondents, you can choose anywhere from 10 to 100. But 10 to 50 is already an ideal. But let's just say you wanted to create a new recommendation, you can explore more than 50. So let's say 30. When we say activation code, it's like what are the mathematical formulas that you wanted to apply in your ANN model? So for the mathematical codes, mhm, I'll open this one so that you can also have an idea how we can compute. You cannot really compute it manually. So you can only compute it using a code for easier processes, but just in case, if you still remember your calculus days, it's continuous iteration like sigmoid with ln, epsilon, and a lot more.
And it's
Mhm.
completely into the unknown.
Yes.
Because like it's so magic, there.
Mhm. Yes, yes. And personally, I don't also know how to compute it manually. But since we have the code already, why
We
not
don't
use
need,
the
we don't
code?
need, we don't need.
Okay.
That's why, for undergraduate Omar and Jimmy, the calculus one, you know what? The software will calculate it for us.
Yes. MATLAB is also helpful for calculus. More
Yeah, of
helpful
course. More
than this
helpful.
one.
Why you have to calculate it manually if you
Right.
just put the tan H,
Yeah,
like a sigmoid and then
true.
Professor, so we still need to put the formulas even if we didn't really even if we
Just the
actually
name. Just put the
Mm,
name.
yes, sometimes they would only, sometimes they do not really require, but for this journal, they actually asked me what were the formulas. So I have to do some research again. But fortunately, Ardwin, if you guys know Ardwin, he already has some formulas for other activation. So I just need to input others. So all right. So if you also wanted to include, let's just say the reviewers ask you to do so, you can just copy anywhere from this one and then from the any of these researches. So two, for these three, all right. So I also just copied their formulas. Okay, so for example, this is your tan H, this is your swish, this is your relu. Again, they're similar to the derivation and all the mathematical operations. So these can be changed. You can change it into sigmoid, relu, elu, and a lot more. So later on, I'll list down all of the hidden layers, activation processes. And then for this one, this is your output layer. The thing with output layer is that it's always better to have lesser output layer or equal output layer and equal hidden layer compared to having more output layers. So it does not necessarily mean that, let's say, two you only have two target variables, so you should only have two of these. It does not necessarily mean like that. It's more of like replicating your output layers. Okay, so this part is more like replicating. And then the activation is also almost similar to the hidden layer. Okay, but the thing is, this code is just for A and N. What if you wanted to change it into D and N like this? You can change it by copying this one. I copied this one, this again, because this is your hidden layer, and then you can just customize your next layer. That means this is your hidden layer number one. Mm, like this. That means this is your hidden layer number one, and then this is your hidden layer number two. So you have two hidden layers. What if you wanted three? You can also input three by copying it again, and then have another hidden layer. And there is no standard at all. For example, you wanted a Lu activation here. You wanted, let's say, sigmoid. You wanted what else? Relu function. It's totally fine. You can also input different hidden layer nodes like 30, 20, 10. It's totally fine. But I would recommend, if you're going to test a lot of hidden layers, I would recommend standardizing all of them so that you can also notice how one activation function and how these nodes would affect the overall model. Okay. So, but just for an example, I'll remove this one. Let's focus on A and N first, because just in case you wanted to check, sometimes your A and N would produce lesser accuracy model. I think I've had about 70% accuracy model for just having one hidden layer. But when I tried inputting another hidden layer, so I have two hidden layers, it suddenly increased into about 90% accuracy. So that definitely helps in increasing your model. Next, what is our optimizer? It's also almost similar to the activation function. It assists us with all the mathematical operations. So again, I'll discuss later on what are the possible optimizer functions that you can also use. When we say loss, it's pertinent to our training loss or validation. Sorry, not training, testing loss rather. Testing loss or validation loss. In this part, we have a lot of mathematical operations again. Gini, if you're familiar with Gini, entropy, and a lot more. But this time we only wanted to focus on entropy, because this is so far the best testing function. Entropy so far is the best testing function when utilizing in an ANN model. Okay. And when we say metrics, we are pertaining to accuracy. ACC means accuracy. For this code, what's important for this code is your epochs. If you remember from our PSO k-means algorithm, we have a total number of 10 runs. So in this part, when we say epochs, we're pertaining to our number of runs, meaning how many times can we iterate our model? Is it going to be 100 times, 200 times, 300 times? So usually it would be around 150 to 200. But you can also search other studies that have a different value, because it already takes a lot of time for you to run 150 epochs. So let's try it. For example, you only run 10 epochs, or you only run the model 10 times. You can see through it. It's pretty quick. But you can notice that Mhm. where is it? Okay. You can notice this is I'll move here. So this is your first run, epochs 1 over 10. Your first accuracy is only 0.0033. So it increases as you run a lot of epochs. So it turned to become 0.1770 in your second run, and then in third run 0.40. So you can definitely see that as we increase our epochs, we can also increase our overall accuracy, because this pertains to our accuracy. This one. Okay, and then this is our training accuracy, and this is our testing accuracy. So let's see if we can really increase our accuracy model. So for example, 50 epochs. Of course, the running time would also increase. So a while ago, we only have a running time of about less than 5 seconds. But right now, we have, let's say, about 10 seconds. So you can see from the 40% something accuracy, we were able to increase it into 88% something. But the thing is, with epochs, we should not find the highest value. So let's say, what if we run 250? If we run 250, most likely you'll have 100% training or testing accuracy. That means you already have an overfitting model. And you can definitely see it from this plot. Let's wait for a bit. If you have an overfitting model, then that means you don't have a good model. So we don't really want it. Okay, so this is what's more important if we're going to take a look at our final model, because this pertains to training model. So if you're gonna take a look at it, it's about 99.51%. It's not that good to have a number like this, because it's like your model is already perfect, but there are no perfect models in ANN. That's why we really need to adjust our epochs. So you really have to find what's the good epoch number. Okay. And then for the next part, and then for this part, it's just about finding our training and testing set. Because when we say print performance, it talks about this part. So let's run it for now. It's going to show your loss and accuracy, like this part. And then for this code, history underscore date is actually very helpful in our plot. So this will be utilized in this plot so that we can know where is our first in which accuracy percentage we can locate our epochs for each run. So this pertains to our runs, and then this pertains to our training accuracy. And then let's talk about the checking of overfit. There is actually no need to explain this one because all of these pertains to the inner side of the coding part. So we just really wanted to ensure that our training and testing set do not meet the overfitting value. So apart from assisting them with the appropriate number of epochs number, we also wanted to check their overfit through these codes. Okay. And then finally, this pertains to our plotting of A and N. So this part, when we say you can actually customize this part very similar to our matplot. So you can also, let's say, B for blue, dash line for the dashes in our plots, and then G for green. You can also use K for block, any colors or any labels that you want. Okay. So if we're going to run it, the model will show a new model. Okay, so every time you run it, you can see that it shows a new model. So for example, this one, it's like this. And then if I run it again, once it finishes the 10 runs, you can notice it suddenly changed. So now you can identify if your model is on the underfitting side or overfitting side. This is actually an example of underfitting. I'll copy this one. This is underfitting. Why is it called as underfitting? Simply because you don't have a good model that is like this. Because the standard model should always be like this. It should have a smooth curve, not like this one. Let's try again a new run. Let's run it again. Mhm. Okay, this is also an example of another underfitting. Because if you noticed, I'll change this one. There is a huge gap between them. If there is a huge gap, and then the green line, because our green line is our testing. So our testing should always be greater than the blue line, which is our training. Why do we need to have a higher green line? So this should be like this. The green line should be like this instead of being below the blue line. Because if your testing accuracy is greater than training, then that means you were able to train your model properly. But what if your testing is less than your training? That means you were not able to train your data properly. Most likely, you have poor, let's say, poor split or poor number of epochs or poor A and N parameters. Mhm.
Understand this one, clear of you. This is very important when you read this. Jimmy, okay, okay, good.
Mhm. Okay. All right. Opportunity is so good. So when we say again split, I'll show it again. This is your split. Okay, so this is your testing size, meaning if you have 40% testing, you have 60% training size. So most likely, if you were able to train 60% and then you got this model, then you have to increase your you have to increase your training size and then decrease your testing size. Because as you test a lot, as you train a lot of data, then most likely you will also be able to increase your model accuracy. So that's another technique. You can also decrease this one, point 0.3 or point 0.2. I would not really recommend point 0.1. So you can just eliminate this in order for you to eliminate the overfitting as well. And a lot of studies mention that point 0.3 and point 0.2 are good for the starting point. But in one of my studies, I noticed that I got good scores in point 0.4 and point 0.5. So you can also recommend some new findings apart from the point 0.3 and point 0.2 usual data splits. Okay. Next, again, is the number of epochs. If you're going to if we're going to take a look at our epochs, we only run it for 10 times. So again, if we increase it, we'll definitely increase the accuracy model. Okay. And then finally, the parameters. When we say parameters, we're talking about from this part, this one, hidden layer, output layer, and your optimizer. So meaning you should utilize a different node. You can try decreasing this one or you can try increasing this one. You can also try a different activation method. This one as well, you can try different activation method. And this one. Okay. So that's it for now. But before we run the model again, let's say once you've already create your own research model, but do you have any questions at this up until this point?
Professor.
Mm-hmm.
Um, for the epochs,
Mm-hmm.
sorry, right? Epochs. Usually, when you have a higher value, your accuracy gets higher, right? So,
Yes, that's correct.
until what point do we, so we just really have to trial and error because it
Yes.
might.
Mm-hmm. Right. Somehow trial and error, but I guess 100 to 150 is the usual standards. But a lot of studies already mentioned 150 is a safe side, so you can start with 150.
Okay, thank you.
Mhm. No worries. Anything else in mind? Any other concerns?
Sir, can I ask the activations there, like the difference
Mhm.
of
Okay.
the formula of it?
Okay, sure. So for the differences, mhm, we're going to talk about these parts from this one. When we're talking about the nodes, we're talking about these formulas. Okay, so these pertains to our nodes. And then for activation functions, regardless of whether it's for hidden layer, for output layer, we only utilize the same formulas like this one, from this one up until this part, up until only up until this part for RMS prop. But if you're also curious to know about all the possible activation functions that we can utilize, so this is like a cheat code. So for hidden layers, you can utilize sigmoid, relu. I'll put relu and elu here. Actually, relu and elu are not good activation functions for me so far, but you can also try just in case.
Oh, I did. It was good in one of my publications.
Okay. Oh, see, you can
One.
definitely see a lot
Yeah.
of differences.
Yes, 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 yes.
It's the poorest performer for me, Doc Yogi.
Depends on the case. Yeah, depends.
Yes,
Yeah.
yes.
Mhm.
That's why I slanted this part, but we can just. Okay, so these are your possible hidden layers. If you're going to transfer them into this part, this one is your hidden layer. You can just copy them as is. Elu, Relu, Softmax, RMS, oh sorry, Sigmoid, and a lot more. Okay, so you can copy them as is, similar to output layers. But for output layers, why don't we have Relu and Elu in output layers? Because they're already a poor performer for output layers. So you can just exclude them. But for hidden layer, you can still use or check Relu and Elu, but for output layer, they're not really recommended. So your hidden layer can also be equivalent to output layer. So it's totally fine. If you notice, they're similar. This one. You can have similar sigmoid, tan H, softmax, and swish. For Adam, for optimizer, it's completely different from your hidden layers and output layers. Why? Because when we say optimizer, we're talking about the overall model. It actually assists the overall model, not just your hidden layer, not just your output layer, but the overall fitting of your ANN model. So that's the importance of each function. Mhm.
Any questions? This is the interesting one, everyone about the
So,
ANN.
Professor, so
Mhm.
basically we
Yes.
have to do like trial and error,
Mm.
which activation or which
Mm.
optimizer that fits
Yes.
with our model. So there
Right.
is no like
Right.
fixed rules of
Mm.
if we use tan or sigmoid and then the optimizer it has to be ADAM or something. There is no like that.
Mm. Right, right. No fixed rules at all. So you can really explore. It's really a matter of finding what's the perfect activation function that works best for your model. So unfortunately, it really takes a lot of time for you to find the perfect hidden layer and output layer.
Thank you, Professor.
Mm, okay. Any other questions?
Sir, so if we use the different combination of it
Mm,
and how we check is which one is better? So
mm,
which variable should we check?
Okay. This one should be checked. I'll go back here. This is the most important part because this first value, the left side, pertains to your training accuracy. When we say training accuracy, you were able to train, let's say, 60% of your model. It's like you wanted to help find the best data that represents your model. That's why in testing, it's always greater than. This is your testing accuracy, and this is going to be your identifier. So once you run all of them, you have to also find, so later on we'll try it again. You'll have to run it like this and then input them. Let's put it here. For example, input them. I'll input this one like this one. So this is your testing part. And let's say once you've already inputted everything, because you have to, although you have already run them 10 times, oh sorry, 100, let's say 150 epochs or 150 runs, you still have to run your model 10 times because this is always the standard. So once you have your average value, let's say we've run them 10 times. So for example, and then you've already calculated the average values. So you have to find the one with highest average testing value. Again, highest average testing value. So you can only focus on this one. The thing is, why do we have to still record the training values? Because probably other reviewers might ask for the differences between your training accuracy and testing accuracy. So it would be best for us to keep our keep our data. But in my latest study, I did not include the training accuracy anymore, and they did not ask for it. So just in case, we have to keep them. Okay, so let's say this is our second run. We have to copy it again. This is your training, and then the right side is our testing set. Okay, so any other questions before we completely run the model? Mhm. All right, no
None
other
so
question.
far.
Oh, sorry.
None so far. Thank you.
Okay, none so far. Okay, no worries. So again, how can we run the model? So let's say you already have this code, you already know the explanation for every line in this code. Let's go in this blank sheet. I'll copy it so that it's completely blank. I'll just remove, mm, let's just use this one. I'll just remove the ones with color. I put I inputted some colors because they are good activation functions in one of the papers I've had. Okay. So the first step is always use this sheet. Why this sheet? Because you wanted to check what kind of activation functions you wanted to utilize. So which among these, this one, which among these would really best fit your model? So in this part, you have to test them one by one. So test your activation hidden layers, sigmoid, ReLU, TANH, softmax, ELU, and swish. So we have a total of 6. If you noticed here, we also have a total of 6. Okay, so you just have to copy them. And then for output layers, we have a total of 4. This is your output layer. This one, activation O or output layers. We have TANH, we have swish, and then in the upper part, we also have softmax, and then we have sigmoid. Okay, and then for optimizer, we must have 3. 3 because we have Adam, RMS prop, and SGD. You can take a look at it in this one. It's Tan Adam, RMS prop, and SGD. Oh, this should be, sorry, this should be, I'll edit this one. Sigmoid, TANH, softmax, and swish. We can utilize this one like this. Sigmoid, softmax, TANH, and then you can create another one. Mm, Why did I input it again? Just a second, please. Mhm. Okay, so for the meantime, let's just say like this. Let's maintain this format for now. So for example, but how about for our nodes? You can choose again any nodes from 10 to 100, but for your testing and training, um, in order for you to find the perfect node in this trial and error part, you have to find a research paper that says, let's say, 10 nodes perform the best among all the nodes, so you can utilize that because this is only for the trial and error part. So let's say we've found, for example, in this study, the best node. Mhm. The best node, okay. For this one, it says that the best node is 30 hidden layer nodes. So we can utilize 30. So you can just make a reference that for your trial and error, you have to utilize 30. That's why our node is 30. So we're going to transfer this one, this blank code, in this part. Mhm. In this part. So you have to change your hidden layer nodes into 30, your activation for hidden layer, this one, sigmoid. Let's test sigmoid first. And then next is activation O, tan H. Again, this should be less than or equivalent to this one. So it's really up to you, but you can just utilize 10. This is already a safe number. And then your optimizer is Adam. So this is optimizer. So you always have to check your hidden nodes first, then change your activation hidden layer, activation output layer, and your optimizer. And then don't forget to check your epochs. It should be 150 for just a safe purpose. But you can also explore anywhere from 100 to 200, but I guess anything that falls above 150 would automatically lead to overfitting. So 150 is definitely a good number already. Okay. So it's, you can already see that this is not a good scenario because you have 0%, 0% testing accuracy. So if you noticed from our model, I'll copy this one. This is another example of bad model. So it's like a flat line. It's like a heartbeat with a flat line. So, but then again, you can also try. Maybe this is just a bug. So let's try if it's going to result in almost similar accuracy.
Same.
Mhm. Yes, I can see that. It's almost similar to 0.0% as
See,
well.
very low.
Yes. So in that scenario, if it's too low, so it's safe to say that you don't need to run everything already. So you can just exclude this one. So you can just mm, let's say what color? Gray. So you don't need to run them anymore. Next stop is for us to check ReLU. How about ReLU? So let's change our activation hidden layer into ReLU. From sigmoid to ReLU, how would it be? So again, it's all about finding a good number and a good accuracy for your model.
Professor, so
Mm-hmm,
if you have a lot of hidden layer, right?
mm-hmm,
The value of the hidden layer should be more than the output layer, the
mm-hmm.
node like the 30 and
Oh,
10,
oh, yes, yes. This should be always greater than or equal to this one. That's correct.
greater than. Okay.
Yes, this should be
Okay.
greater
Okay.
than or equal to this one.
Okay. Thank you.
Okay, no worries. So you can also see from this model that we have a very poor value again. So most likely in our next run, we'll definitely have almost the same result. So you can exclude this part already. You can exclude your ReLU and then test your tan H. But in this scenario, I think it would be better. Let's say I'll change my activation O, for example, softmax. Okay, so for example, this one, I'll try sigmoid, softmax, this one. I'll change it into sigmoid, softmax, and then RMS prop. So let's see if it's going to have a different result.
Oh, gonna
I
be
hope
good.
so.
This one gonna be good, definitely.
Hopefully. Yeah, sigmoid and softmax are always a good combination, by the
Yes,
way.
Sigmoid and Softmax. Those two are
Mhm.
so powerful.
Yes. But sometimes they lead to overfitting. So you should always be wary of that.
Oh,
So
this is
in this,
overfitting.
mhm,
Mhm.
yes, this is overfitting, but it's fine for now. It's fine for now. Why? Because we're still in the trial and error part. We're not yet in the final selection of our activation function. So you can just copy this one for the meantime. Okay. So you can just copy them so that we already have a standard and a benchmark for our activation function. And then you can run it again. So why is it overfitting? This is your model. You can see that the green line is almost close. It almost touches the blue line. So if it almost touches, then most likely there is definitely um very minimal space for the error, and we don't really like that in the model because again, we in ANN we don't have a perfect model. So there should be a little bit of a gap.
So can you show like one, the final one that is a good one in your paper?
Oh,
No,
okay.
yeah.
Mhm.
Let later on, everyone, you have to show something like show the one in your paper. Sustainability.
Okay. Sorry, not this one.
Wow, the original paper.
Yes.
Ah,
Okay,
this
so
one. Look at this. Yeah,
this one is already a good model, I would
super
say.
good.
So you can definitely see from it because if you're going to compare, there's a lot of what do you call that? There's a lot of
Zigzag,
spikes. Yes, the
zigzag, yeah,
zigzag
spike.
line. We don't really want that. We want it smooth as much as possible. So although there's a little bit of zigzag, it's definitely still smooth. And you can see a huge, not huge, sorry, just a small gap between the blue line and the green line. And it another thing to consider is that I forgot to mention it. The green line, this one, should always be above the blue line compared to this model. Compared to this model, it falls below the green line. So sometimes it can be tagged as underfitting, but it's not underfitting. This time it's overfitting because, as you may have noticed, we have a very high accuracy rate. So that means this is still overfitting, although it's below the blue line. It's called as overfitting and not underfitting because of the accuracy. Okay. So any questions up until this part when it comes to plotting our accuracy?
So after that, what will be the next? After you finish everybody finish the
Uh,
Excel file.
Okay. So let's say you've already found the best activation function. So just for an example, in the scenario, for example, I chose the one with the highest three testing accuracy values. So that's for tan H, sigmoid Adam, Elus sigmoid Adam, Swish sigmoid Adam. And it's actually you can actually find that some similarities because although we've changed the activation for output layer, for example, this one I changed it from sigmoid and then to softmax, I still receive almost similar activation function with the highest accuracy model, this one. So you can already utilize this part. So let's say tan H, LU, and swish. That means you're going to copy it in this one, tan H, LU, and swish. So that would be your final activation. Why did we choose 3? It should always be a standard. Whenever you choose your activation function, it should always be at least 3. At least 3 if you have only let's say one target variable, because you have about 2 target variables. So I'm unsure if you're going to separate ID from IV, but if you're going to combine them, so I would suggest you can just utilize 2. It's already fine if you're going to combine again ID and IV in one research paper. And then for activation O, we have sigmoid and softmax. It's actually okay for this one. For example, we have tested sigmoid, softmax, tan H, and then switch. But then again, these are the top 2 with the highest number of testing accuracy. So you can utilize sigmoid and softmax if it received the highest number. And then sigmoid here, but you have to create another Excel sheet for softmax. This one. If you notice, we have the similar activation H. We have still tan H, LU, and swish, but we have a different optimization activation function. Softmax for this Excel sheet, and then sigmoid for this Excel sheet. But it's also up to you. You can also bring them into one Excel sheet, but just for proper documentation purposes. And then how about for your optimizer? It's always a standard to utilize them, ADAM, RMS prop, and SGD. So actually, there's no need to test them at all. But then again, if you're going to have a very long model, you can just utilize 2. Very similar to activation H. You can just utilize 2 if you're going to opt for a very long research model. Okay, so let's say now that you have this one, you have to test it again. So this is already um your this is already a path towards your final model. So this one and not for this one, because again for this one we just wanted to find what are the best activation functions that we wanted to utilize here. So for example, I'll copy this one. We're going to test these parameters first. Why did I input blank? Because you have to input what is your feature that you wanted to test. For example, EE. You can also change it into U, PV, PS. So do not forget that for every sheet you also have two two sheets for every feature, because you need to have sigmoid and softmax activation output layer. So this one is for EE softmax, and then this one is for your EE sigmoid. Mhm. And how can we apply it again? So don't forget to double check this part. If you're going to test EE, you should it should always be EE. And if you're going to test ID, this should always be ID.
My your voice. Sorry, we cannot hear your voice.
Now, Dr. Yugi?
Okay, now okay. Yeah.
Okay. All right, sorry. So, in number of nodes, sometimes you can just utilize any tens values. So from 10, 20, 30, this one 30, 40, 50. Why did I utilize anywhere from 10 to 50. It's also based on a research paper. So it's actually from one of my colleagues. He mentioned that it's one of the best nodes, so from 10 to 50. So you can also utilize that one, but you can also go beyond 50. You can also check, let's say, just 20, 30, and 40. It's totally fine. At least three. I This should also be at least three. And if you have if you have lesser number of nodes, you'll also get lesser accuracy model. But if you also have higher number of nodes, let's say 50, it's prone to overfitting as well. So you also have to find the balance among all the values. So you're going to test it, change this one to 10, and then change this one to 10 each, sigmoid and Adam. This one should be 10 each, sigmoid, and then Adam. And then you should run it. And you have to run it 10 times. After running it 10 times, you'll have your average accuracy for training and testing. You'll also have your standard deviation for both. And then after running them, you have to change it again to ELU, sigmoid, Adam. So let's say we've already run everything. Change this one from tan each to ELU. Why ELU? Because we're going to talk about or to fill in these blank. ELU, sigmoid, and Adam. These.
How good is good, Maela?
Mm,
How good is good? I like after you finish all of that,
mm.
how you decide
Oh,
that one, the final one.
the final model.
Yeah, which
Oh,
one?
I would say it should be around 90% accuracy.
Not
It
95.
mm,
No,
90% to 97%
okay, yes, just
is
around that, right?
already good.
Yeah, yeah.
Because if it goes beyond 97%, I think my accuracy model is about 97.5% something. It's already fine. But they might question you so that you'll sometimes let's say in these
Yeah, they might question, right? I'm thinking like
mm,
how that's also like one unfinished question. I forgot to ask that to Dr. Farah, and then yeah, how good is just already good. I don't know how to cut that
yes, usually around 90% to
to
97%.
97%. Okay,
And also, yes, Doc Yogi, and also
the figure,
the
yeah,
yes, the figure. This is
yeah,
really important. So this somehow backs up your number, even if they
yes,
ask you if it's
yes,
overfitting. You can just tell them that it's
yes,
not with a
yeah.
good figure.
Mhm. How is
Okay.
that, Jimmy? You like it? This is our world.
Okay.
This is totally how is that, Myla? Very different from Eric. Very, very
Yeah.
different.
But sir, if we find the best model and how is we report it and how we
Oh, okay.
say, okay,
Okay.
the good of it is what?
Okay. Okay.
Mm,
The
okay.
implication, Maela, for example, like after you already got 90 something percent, how we interpret the data. Like, can you show like one example of your,
Mhm.
I think your PhD dissertation, what about that? Do you have the file?
Mm. Oh, I did not utilize the ANN, but for this one, for Siargao, I utilize ANN for
Oh, okay.
this part.
Yes. Okay. Already published, right? This one? Yeah.
Yes, yes.
No, no.
Our one
The
last.
no. The final table and then how you the implication of that one to the in the Word file. Okay, this is the
Mm,
final one. Okay,
okay, yes. Mm, mm,
the paper, just the full
because
paper.
the paper.
Yeah, the
Oh,
full paper,
this
and
part.
yeah, because he for example, you already got okay this one, right? This
Mhm.
is the final one.
Oh, I actually utilize another technique, but this one is for ANN.
What technique did you use this one?
Oh, I utilize another algorithm, logistic regression infused with feature selection in this part. So this one, just this one.
This is not me. Oh, this is like another of the industrial engineering, like.
I really
Okay.
wanted to explore that. That's why I made this
Yes, that's
paper.
yeah, I know you're the daughter of the Dr. Farah. That's why like you can do that. But for me, this is like another world. Okay,
Don't
okay,
worry.
just tell us the implication. Just the end.
Mm. Okay, sure. So in your model, you don't need this one, PI, RFE, and LASSO. This actually pertains to another method. So you can just erase this from your mind. So let's just say everything is A and we can just consider this first row. Okay, so again, we'll just consider the first row for A and N. Why did I choose this one? Because it has the best or the highest testing accuracy. That's always what we're aiming for, to find the highest testing accuracy. But then again, let's just say, what if your testing accuracy went beyond 98%? Then you have to find another, or you first, you have to run your model again and then see if after another 10 runs, it's a process called as holdout method. If you run it first time for 10 runs and it went beyond 98%, then you have to run it again 10 times. So that means you already have 20 runs. But if you run it again, then it still went beyond the 98%, then you have to completely remove all the activation functions. You have to replace them with another one. So once you have these threshold, you can find your most important feature by finding what kind of input layer did you utilize in this part, this one. So this is your most important feature. So that means every time we remove EE, for example, this is EE. Every time we remove EE, our testing accuracy increases. That means that's how important the EE is. So again, in ANN, it's like in a vice versa, in a complete different explanation. It's not about removing the model, then you'll have lesser testing accuracy. It's more of once you remove your important feature, you should definitely have higher accuracy. And then for optimizer, I did this actually comes in this one training, testing, nodes, hidden layer, activation, output layer, and optimizer. Everything that you have inputted from this part. And if you're going to check back with our Mm, this one, for example, if we've already run everything, EE, PV, and a lot of features, you should receive the highest testing accuracy. For example, this one has the highest testing accuracy. Just for an example. So that means this is your best parameter. This is your best A and N parameter. So this is what you're going to transfer in a table like this one. So this is your average testing accuracy, this one, and then this is your standard deviation. So that's how you can find the best model. So it's all about finding the highest average testing accuracy. So, mhm. So that's it up until that part, Takyogi. Any other questions?
How to read like the can you
Mm,
show like the original model, and then how
mhm.
to read the can you show the one that published in the the one in Sherga already published in Science Direct, right?
Yes, yes, this one, Shergao.
Can
It's
you show like
already published.
can you show the one that in Science Direct?
Oh, is it this one?
That's the
This
same
one,
date.
Shergao?
Yeah. Wait. Let me just open the, let me open my no,
Mhm.
no, the one that the one that in disaster risk reduction.
Okay. Uh,
Do you have the? Okay, I have the file.
okay. I think I don't. Oh, okay. Sorry. It's this one, Dr. Yogi?
For a while. Yes, that one. Can you show
This
like
one.
how's that? Yeah, can you show just scroll down like the model, that one, like
Oh.
okay, yeah, just the model. Okay, this
Mm.
is the model. Okay. Okay, imagine, okay, everyone, this is the model. Okay, this is the transformation from SEM to ANN. Now, okay, she already figured it out. And at the end of the day, from ANN, what's the most important?
Oh, in ANN, it's hedonic motivation.
No, see,
This
see,
one.
see. Now you got it. You know what? When hedonic motivation, can I see the result of the published one? The ANN.
Oh, this
Okay,
one.
this one is like this one. The best one is
Mm. Oh, the
no,
PBC.
yeah, right. But
Mm.
if you go back to the ANN result, it's more fair actually in ANN.
In ANN, my
No,
PBC is
the
just.
no no
Hmm?
the published paper. Yeah, that one. Yeah,
Oh, sorry.
yeah,
This
this one.
one.
See,
Ah.
see, look at that one. Most important feature in here is actually the HM. You know, it's not the
Mm.
PPC in here, but it does more make sense because like if you want to go from a place, an island, beautiful island that's just being hit, you know, by the super typhoon, you know, like the best one actually like because of the hedonic motivation in
Mm.
this one. That's actually how
Yeah.
we read it, Jimmy. You know, based on that, because we actually really focus on the super feature selection. Everyone is
Mm.
equal, like I told you before, like you put everything equal and they fight each other in those hidden.
Right.
Yeah. So now we found like a better model. But what about the indicator inside that one? I was thinking about that, Mela.
Mm. Oh, for this paper, Doc Yogi, I utilized feature selection.
Feature selection, right? The next one, is there a more crazy one? The next one, like indicator selection. And-
Could be.
but
Could be,
yeah,
but
how?
they should not overlap.
Yeah, but yeah,
Let's say
another
if
one, like
you're,
yeah,
yeah, it
yeah.
could be possible, Doc Yogi, but let's say if you've utilized factor loading and then utilize feature selection again, it's not recommended. So you can just utilize one of them.
Yeah, because like yeah, I was thinking, okay, but I was thinking like if we just change everything into the factor loading, but cannot be right because
Mm.
factor
Oh,
loading the data is just how is that only one, right? Only one data.
oh,
Not
for the factor loading, Doc Yogi, it could be possible. So because in factor loading, you're going to eliminate the ones that are below 0.7. So you can utilize, for example, HM. I can just utilize from HM1 to HM7. And then
I
this is,
see. I just
yes,
do
it's
the another
possible.
ANN again. Just do
Yes, yes.
another ANN. Ah,
But
but
you should stop in this part. You should not run other mode.
yeah, but but the problem was like from this one, you know, from the HM, the data is only only seven in the Excel
Mm,
file. How is
mm,
it? How is that possible to run the ANN
mm.
again with this? It's not possible, right?
Oh, it's possible. We can just find the average value because in ANN Dokyogi, let's say we will going to choose HM1 to HM7.
Oh, so
We
that
just have
as just
mm,
imagine that one as a feature, you know, like that one.
mm,
Ah, got it. You mean like HM1, 2, 3 in the Excel?
mm,
Yeah, just open
yes,
one Excel.
yes.
Yeah.
Mm,
Ah, I got it. So like you put that one as like a feature. Treat that as a feature. You mean like that?
mm,
And then put
yes,
average. I see.
right. This is already average, but
Yeah,
we
yeah,
did not utilize any methods yet, just the raw data.
yeah. Okay, but
Mm.
another greater, I don't know, cuter, I don't know, like crazier direction. Like you after you figure it out HM. So which fund of HM? I was thinking like
Oh, okay. Oh, once we have this part, Tokyogi.
yeah, like you do
Oh.
another one. You know what I'm thinking of? Like you do another one and treat one one for example HM1 as a feature.
Oh, you can actually just separate them, Dokyogi. It's possible. So you can just not you can just eliminate the HM instead of treating them as HM. Don't average them. Don't find the average values, and instead just utilize HM1, HM2, HM3. But it would be quite a lot.
Oh yeah, it's crazy. Yeah. I was
Yeah.
thinking about that. Like, it's how is that possible? Like to test
Mm,
like all of that one by one. That's crazy.
yes. It might take a number of months.
Yeah, it might take months,
Mm,
yeah, it's possible, but it will take months,
mm,
to run that. Oh, I already got
mm.
like
Too much of a headache.
okay, well, for today, please just stop at that.
Okay.
Okay. So everyone, you learned a lot in ANN. I think that's most likely all about the ANN, right?
Mm,
Myla,
mm.
anything else
Yes,
from
Doc
the ANN?
Yogi.
I think that's already all. Yeah.
Yes, it's already that's just about it. The ANN. It's more easy to interpret ANN than PSO K-means.
Yeah, it's easier actually to interpret and and looking at the result, I like seeing the result more than that. But doing that, everyone, you have to click run one by one, click
Yeah.
run
And
by
then they
one.
have to wait again
You have to
because
wait
we have to
again.
run
You have to
epochs
click
of
and
it.
run again. You have to click again, run again. Like, it will take like last time I did something like that, it took me like months, like 2 months, perhaps like what? Yeah, I think around that one. Yeah.
Yes, but you can do other things apart from that. So I often watch
Yeah.
movies on the side.
Yeah. Korean movie.
Yeah.